Okay, this is day 49. It's Hess's law and enthalpies of formation or heats of formation. We're not going to do bond energies in this particular lesson. It's Friday, November 1st. This is due on Tuesday. Try to get as much of this done by Monday as possible. It's a fairly long assignment, and we'll add bond energies on Monday and finish up this topic. So question one, what does thermochemistry study? So it studies the energy changes in a chemical reaction by measuring the heat that enters or leaves the reaction. So we isolate the concept of heat in a constant pressure chemical reaction. That's one that you carry out in the open atmosphere where the pressure at the atmosphere doesn't change. That's called enthalpy. And we're interested in changes of enthalpy. Delta H are measures of the heat that goes into and comes out of a reaction. So we speak more of delta H than we do change in enthalpy than we do of heat specifically, but they really are the same thing. Okay, so two, what are the four ways we can compute heat? So calorimetry, it's what we did in our lab. That was constant pressure calorimetry. Constant volume is called bomb calorimetry. And we'll talk about that. It's computed somewhat differently than constant pressure, so we'll be sure that you're clear on what those differences are. Then there's Hess's law, which is kind of I think of it kind of a chemistry puzzle with equations. And then there's enthalpies of formation, which is actually much simpler than Hess's law and does the same thing, but you don't always know the enthalpies of formation, where sometimes you do know the information that's in Hess's law. That's why you might use one over the other. It's just a matter of what information that you have. Finally is bond energy. That's not the best way to do it. It's an approximation, and we'll get into that when we talk about that on Monday. Okay, so next up, what is the definition of heat or enthalpy of formation, delta F, and how many moles of product are shown in an enthalpy of formation? Well, answering the last question, enthalpy of formation are always for exactly 1 mole of a chemical reaction. So the enthalpy of formation, and it's delta H F, enthalpy of formation, is simply the energy required to form a chemical compound from its basic elements. In their most stable form. Okay, so let's get into some examples. I do want to make an important correction here too. There is a typo. So one thing about these videos, it's a chance for you to pick up typos that may have appeared that you may not otherwise have noticed. Okay, so to make methane, CH4, it requires 1 C and it requires 4 H's. There they are right there. Now, carbon in its most stable form, as we talked about in class, is a solid. And it's specifically, there's many forms of carbide. There's graphite, there's diamonds, which is the hardest substance on Earth. There's buckyballs. There are all kinds of different forms of carbon. But in its most stable form, carbon is actually this very soft material that's right here in the tip of this pencil called graphite. And it's so soft that when you rub it across a paper like that, it leaves a mark. But that is carbon's most stable form, and we're going to prove that in one of the questions a little bit later on. So what this means is you have to write these equations so that they produce exactly 1 mole of the product. And if you do that, what will happen is 74.8 kilojoules per mole. So this up here is red, kilojoules per mole of the compound. So 74.8 kilojoules for every mole that's made will come out of the reaction because it's a negative sign. Remember, enthalpy is like a bank account. If it's negative, it's going out of the bank account. It's going out of your bank account or out of the system. And this chemical reaction is the system. So that's what an enthalpy of formation is. So let's look at water. Water is made from hydrogen, and its most stable form. It's a diatomic molecule. It's not just a single hydrogen atom. Also from oxygen, and oxygen also in its most stable form is a diatomic molecule. And to produce 1 mole of H2O, this would be the equation. Now, we've written this equation before as 2H2 plus O2 gives you 2H2O. But remember, in this equation, it must produce exactly 1 mole. That means we actually have to divide that 1 that was in front of the oxygen, that gets cut in half. So this is the only time in chemistry that you'll find fractional coefficients. And that's because you must always set the product formation to 1 mole. So sometimes you'll end up with fractional coefficients. Okay, that was for water as a liquid. This is for water as a gas. It's the exact same equation. Where you find a difference is in the enthalpy of formation. Since water is at a lower energy, that means it must release more energy to get to that lower energy. If it wants to fall down to a lower energy, it has to release more energy and let more energy go. So you'll notice that the enthalpy of formation for liquid water, 285.8, is less than the enthalpy of formation for water in gaseous form or in vapor, or you can think of that as steam or vapor. This has more energy in it, and therefore it doesn't have to let as much energy go in order to reach this state. If it wants to go from this state and condense down into liquid water, it has to let about another 44 kilojoules of energy go. So that's the difference between these two numbers. Carbon dioxide, again, we use carbon in its solid form, and that's graphite, plus oxygen, and that will give you CO2. Again, always put the states of matter in. That's important in these equations. And then we have ethane. So you got 2 carbons, but carbon doesn't come in a molecule of C2. It comes in 2 separate carbon atoms. Again, that's graphite, the solid there. And then you need H6. So you need H2s because that's the most stable form of hydrogen. And to get H6, you have to have 3 of them. So that would be the equation for ethane. And there it is. It's minus 84.7. Okay, for propane, it's 3 carbons, so you need 3 of those graphite carbon atoms, and then you need 4 H2s to give you the 8 right there, and that'll give you C3H8. Now there is a mistake, and you need to correct this. The enthalpy of formation for propane is not 2,220. As you're going to find out, that's a number we'll come up with one of the questions later on. That was a typo, so I apologize for that. It's negative 103.85. The other place you could have found that is on this purple sheet. So I want you to keep this handy when you're doing these problems. These are all enthalpies of formation for different compounds. So if you look over here at propane, there it is. It's minus 103.85. So scratch the 222, negative 2220, and put in this number right here. And finally, for butane, you need 4 carbons and you need 5 H2s, 5 times the H2 molecule right there, and that will give you butane. All right, let's keep going here. And this is all what we've done in class today, so we're moving a little faster through this. What do the enthalpies in the table above generally tell you about the energy in a reaction system when a chemical compound is formed? Generally, things in chemistry tend towards lower energy. So these are all exothermic. They all have negative signs. The heat is going out. That means that the products end up at a lower energy level than the original reactants were at. And generally, things in chemistry want to go to lower energy. As I said a number of times, there's a notable exception to that or condition to that we're going to study later on when we get to a different subject called thermodynamics. This subject is thermochemistry. So thermodynamics will understand what that other factor is. But generally, things do want to go to lower energy. Number 6, why is enthalpy of H2O liquid? Again, if you see that, it's not a 1, it's an L for liquid inside that parenthesis there. Why is the enthalpy of H2O liquid a more negative value, 285, than H2O gas at 241? And I just talked about that because in order to become a liquid, Liquids are at lower energy than gases, which have more energy in their molecules, and therefore you have to give away more energy here than you do here. To become a liquid, have to give away more energy, has to be more exothermic. Okay, now we're going to work a few problems in the second of the four methods that we talked about for determining the energy or the enthalpy of a reaction and therefore its change in energy. And this is using Hess's law, and it's kind of a little bit of a puzzle of rearranging equations to get the enthalpy of an equation for which you don't know it. So you come up here and just make a little correction. That should be a question mark. So let's say we have this reaction. We don't know the enthalpy, and we want to know the enthalpy of this reaction right here. But we have two related reactions for which we do know the enthalpy. If you can rearrange these in such a way that they form this reaction up here, then you can determine the enthalpy of that reaction. Now, in the real world, they know the enthalpies for pretty much everything now. However, this is a principle of chemistry, just as the associative property or distributive property is a principle of algebra that you learn. And so the purpose of this is not to discover anything that's not known. It's just to basically teach you how you can manipulate equations to get information for a new equation. Okay, so we have these two. We know the enthalpies. Now, I've copied them on a separate piece of paper. You might want to do the same. I'm not sure this is enough room. It probably is for this problem, but for some future problems, you might end up with 6 or 8 equations down here below in doing this, especially if you have three equations rather than just 2. So I would recommend doing this on line paper. So I'm going to go ahead and uncover my line paper, and there you see the same reactions. So this is our target reactions, what we're trying to find the enthalpy for. And these are the 2 reactions that were below that have the known enthalpies. And one thing I always do is I label them. I give them numbers 1 and 2 so that you don't get your reactions confused. And that's especially important if you have 3 equations. You want to be sure you don't get them confused. So what we're going to do is we need to find a way to get these 2 equations to form this equation. So one strategy I would use is you look at this equation and you see that it has C all by itself. And what I tend to do, it's just my little technique, you don't have to do this, I circle the arrows because I want to be clear on where the right side of an equation is and where the left side is. Because this can get a little bit messy when you start crossing things out and adding things and so forth. It can start to get a little cluttered. All right, so here we go. So we want to have a C on the left-hand side of our final reaction. So we look for where we have C's in these 2 reactions, and it's only in one place right there. So what we determine is we do not need to reverse this reaction. Let me just review the 3 things that we said we could do to these reactions. We can reverse a reaction. That means put the products on the reactant side and the reactants on the product side. So in other words, you could flip this around this way. So the CO2 comes over here, and then the C and the O2 go to the other side. What that does to the enthalpy is it simply changes the sign. It would go from negative 393.5 to positive 393.5. The other thing you can do is you can multiply through by a factor, just like you can an algebraic equation. So for example, we could multiply this by 3, we can multiply this by 3, we can multiply this by 3. If we do that, first of all, if you do that, you have to multiply everything by the same factor. You can't just multiply one of them. So 3, 3, 3, and this is just my example. Then you would multiply this by 3. It would stay negative in this case, but it would be negative 393.5 times 3, whatever that comes out to be. The other thing you can do is you can add elements that are on the same side of the arrow. So if we look at the arrow here, we have an O2, that's one O2 molecule, and a half of an O2 molecule. So if you were to just happen to add those together, you get 1 plus a half, or 1 1/2, or 3 halves. So you can add them if they're on the same side of the arrow. If they're on opposite sides of the arrow, you can subtract them. So I don't have any example of that right here, but if you had a CO2 on this side and a CO2 over on this side somewhere, you could subtract those. They basically cancel out if they're on opposite sides of the arrow. So you can reverse, you can multiply. Again, this is all very much like algebraic equations, and you can do adds and subtracts. And by doing those 3 types of operations, what you want to try to do is with these two equations to recreate this equation. So getting back to where we were, we see that we have C already on the left side of the arrow, and that's where we want it. So we know we don't want to reverse this first reaction. So we don't want to reverse that. We're going to keep that where it is. Now, what we need to do, and there was a second typo that I should have pointed out. Let me do that right now. And this should be CO2. And I made that correction in class, but let's be sure we make it right now. So that should be carbon dioxide, CO2. Okay, so go ahead and make that correction. Now, what about this one? Does flipping this one do anything for us? Well, we see that in our final reaction, we want CO, carbon monoxide. And we see we have CO over on the left side of the arrow in this reaction. So that would indicate to us that we want to reverse this reaction. We want to get the CO over on the right-hand side, so it'll be like this CO over on the right-hand side of our target equation up there. So what I'm going to do is I'm going to draw an arrow. I do this. I both draw arrows and I relabel. So instead of equation 2, this is equation 2a. And all I'm going to do is reverse this side. So the CO2 on the right side comes over to the left side of the arrow. That's the gas. Then the arrow stays there. And then everything on the left side goes over to the right side. So we have CO gas plus 1/2 O2 gas. All right. So we did that. Now, when we did that, we have to take this enthalpy and change the sign. So it's still 283, but it becomes positive. So now delta H equals positive 283 kilojoules. Right? And then the last thing I usually do is just very lightly draw a line through this whole thing. You don't want to make the mistake of using this anymore. You're done with that. You've changed it. So we now have equations 1 and 2a to work with. Now let's see if these two equations as they are will get us to this equation. So we already said we had C, carbon, on the left-hand side of this arrow. So that matches up with the carbon in the target equation right there. Now, what about CO2? We have CO2, and nowhere does CO2 appear in the target equation. But we notice we have it on the right-hand side of equation 1, and we have it on the left-hand side of the arrow of equation 2a. So those two will cancel out. They will subtract away. So they just go away. So we've gotten rid of that. All right. What about CO? Let's see if in either of these we see CO. There it is right there. So I'm going to circle that. And that's in our target equation up here. That's a gas. So we've accounted for the CO on the right-hand side of the arrow. And as I told you, I like to circle the arrows to be sure I don't lose track. And it's on the right-hand side there. So the only thing we have to deal with is oxygen. So on the left-hand side of this arrow in equation 1, we have O2. That's one O2 molecule. And down here on the right-hand side of 2a, we have a half. Since they're on opposite sides, that means they subtract. So 1 minus 1/2. This up here is going to be 1/2. And this one's going to go away. So the 1 minus 1/2 equals 1/2, and there's the 1/2 right there on this side, because that was the bigger of the two numbers, so the 1/2 goes over there. So now we have 1/2 on the left side of the arrow, and we have it on the left side of the arrow there. So we've accounted for everything in our target equation, so we're really done with the problem, or at least with rearranging the equations. So we have C plus 1/2 O2, and on the right-hand side of the arrow gives us CO gas. So we've met our target equation, and in doing so, we've changed our enthalpies appropriately. So the only time you change an enthalpy is if you either reverse an equation or multiply through by a factor. The act of adding or subtracting compounds or elements does not change the enthalpy. You notice when I added 1 plus or 1 minus 1/2 to get 1/2 there, we didn't do anything with enthalpy. That doesn't affect the enthalpy. That's really just like cancellation in algebra. You're just canceling things out. So now what we're ready to do is do our arithmetic here. And so we're going to say that negative 293.5 minus 283 That's going to give us a delta H of reaction, which equals negative 110.5 kilojoules. And that is the answer to that. Okay, so that's how you do a Hess's law. They're not really that hard. Some of them can be tricky if they have a lot of equations and they're very complicated, but the principles are pretty simple. 3 basic principles you follow to get the answer. Okay, so now we're going to move on to number 8. And what it gives us is a reaction, and we want to see what the enthalpy change is when carbon as diamond form, the hardest substance on Earth, becomes carbon as graphite, which is very soft. That's in the pencil lead right here that is on the paper. The 2 equations we have to work with are the enthalpy of formation equations for carbon dioxide using carbon graphite plus O2 to give you CO2, and carbon diamond plus O2 to give you CO2. And here are the enthalpies associated with those. So we want to use these 2 equations to arrive at this. And I should add right here what we're trying to find ultimately is a delta H for that reaction. So we're going to put a question mark there. That's what we're looking for. Okay, so I'm going to uncover that I've written this on a piece of paper already. And let's go ahead and see what we have. Well, this one's pretty straightforward. I'm going to circle my arrows so I'm clear which is on which side. And we see we have graphite over on the right-hand side of our target equation. This is our target equation. And so graphite's on the right, so we're going to take number 1, we're going to reverse it. I'm going to call that 1A. And I'm going to take the CO over here and move it over to the left. So CO2, gas. And then I have the arrow, and then everything that was on the reactant side is going to go over to the right. So that's C graphite. Plus the O2 that's with it. Okay, now when I do that, I have to take this up here, the delta H. I'll just write it down below here, give me a little more space. Delta H equals, now since I reverse the equation, I change that to a positive sign. So it's plus 393.5 kilojoules. Okay, and then the last thing I do is I lightly put a line through this so I don't make the mistake of using it again, because that equation's done. We've now transferred it to this. So now we see what we have. On the left, we have diamond. That's good. That's what we want. And on the right, we have graphite. That's what we want there. So hopefully everything else cancels. So I'm going to circle all of my arrows. So on the right side of this arrow, I have O2. And on the left side of this arrow, I have O2. So they cancel out. Okay. And on the right side of this arrow, I have CO2. And on the left side of this arrow, I have CO2. So they cancel out. So everything canceled out except the carbon diamond and the carbon graphite to give us our equation. So now we just have to do the math on this by adding negative 393.4 to positive 393.5. And if you do that, you get a delta H of reaction for this of negative 1.9 kilojoules. So that means it's an exothermic reaction. But what it also means is that when you go from diamond to graphite, you're lowering the energy. And remember, in chemistry, things generally want to go to a lower energy. That means that this reaction will probably take place, and in fact it does. And over time, diamond will turn into graphite because it is at a lower energy. Okay, so that takes care of that one. Okay, now we'll move on to number 9. And this is our target reaction. And maybe you can quiz yourself and see what those names are. They're covalent bonds. And so you use the prefixes, the mono, di, tri, tetra, so forth. Anyway, I'll leave that for you to do. So we're trying to find this enthalpy from these 2 reactions. I should add a solid here. This is solid. Okay, and there's the enthalpy. So again, I'm going to cover my line paper. I prefer to do this on line paper. All right, and we're going to go ahead and label these equations 1 and 2 right there. All right, so what we see is we have P4 plus 3O2 plus P406 here. And again, I'm going to circle the arrows, be clear which side is which. And there we have P4O10 and oxygen and P4. So we don't see any P4 up here in the target. So we know that these P4s have to cancel out. The only way to do that is to make one of these two equations reverse. Well, since we have P4O6 on the right-hand side of equation 1, and we see that it's on the left-hand side of our target equation, we're going to reverse equation 1. So I'm going to just draw an arrow and call it 1A, and just flip this thing around. So it's P4O6. Okay, and there we go. We flipped this one around here. That means we've got to change this enthalpy, so all you do is change the sign. So delta H equals positive 1,640.1 kilojoules. Just put the little plus sign just to emphasize that we changed that to a positive number. And since I went ahead and changed this first one, we're not using it anymore, I'm going to lightly put a line through it. So these are the two equations we're working with. So let's see how things cancel out here. So we need to have P4O6 on the left-hand side of the arrow up here. That's our target. So we have it right there. So that's good. That's taken care of. And now what about P4O10? We need that on the right side up here, and we have it on the right side of equation 2 right there. So we've taken care of those two. Now what about the oxygen? Well, we have 5 O2s on the left side of the arrow, and we have 3 O2s on the right side of this arrow. So 5 minus 3, because they're on opposite sides, is going to give you 2. And the 2 goes on the side with the bigger number originally. So we're basically going to change that to 2 O2s. And this whole thing goes away. It just subtracted out. 5 minus 3, that went away. So that left you with 2 O2s right there. And that's what you needed in your equation up here. So everything's done. We've used these two equations to create this equation. So now we just do our math down here. So it's negative 2940.1 plus 1640.1. And that's a pretty easy math equation. That's going to give you a delta H of negative 1,300.0 kilojoules. Okay, and that's the answer. So that's a highly exothermic reaction right there. Okay, now we're going to move on to the third of the 4 methods for determining the energy in a chemical reaction through its heat. And you're going to find this one easier than the Hess's law. So we're going to start off with an equation for propane, and it looks like my arrow floated away here. Maybe it's made out of propane and just elevated there. So I'm going to put the arrow back there. So here's a balanced chemical reaction of propane plus oxygen combustion reaction, right? We'll give you carbon dioxide and water. And we're trying to figure out what the enthalpy of reaction is for that. So to do that, you look at your notes, and let me grab mine. And there's a formula. I'd like to make a correction in the formula. So there it is for the enthalpy change. It is, and it's not the summation really. You could put a summation there. It's really the change. It's really the delta H. It's just another way of finding delta H of the reaction. And what you do is you sum all of the products. This is at standard state conditions, so we're going to assume that unless told otherwise, and you won't be. So the enthalpies of formation of the products. Now the N means you have to multiply by any coefficient that's in front of that number. And then you subtract from that the summation of the enthalpies of formation of the reactants. And again, any coefficients in front of any of those compounds you have to multiply by. So let's just go ahead and see this equation in action. I recommend, in fact, I almost insist, in fact, I do insist, that you write down formulas like that every time you do a problem. Eventually they stick in your mind and they become natural. So for this one, we've got delta H of reaction, RXN, is going to equal the sum, that giant sigma, that's capital sigma, Greek letter, of the, and it's the number of moles, and it's the delta H at standard conditions of formation. She should have put that right there. Of the products. So that's on the right-hand side. You got to be careful when you do this equation. It's a very common mistake to put the reactants are on the left side of an equation, and this is on the left side of this equation. So be careful. The products are on the left side, and the reactants. You're going to switch these two around. In other words, when you write the equation, minus the sum, add them up, number of moles times the delta H of formation at standard conditions of the reactants. And you will see what that means and how easy that is to use here in just a second. Okay? All right. So these are our products. These are our reactants over on this side. So what we're going to do is we're going to start on this side. And I use block parentheses because you're going to need regular parentheses inside. So we have 3 times the enthalpy of formation of carbon dioxide. So it's 3 times, and all we do to get that is go back to the front page of this assignment, and there's carbon dioxide gas. These are all enthalpies of formation. Remember the correction we made right here at the beginning. And so if you didn't make that correction. That negative 2220 should be negative 10385. So we're going to use that in just a minute. But for carbon dioxide, here it is. It's negative 393.5. So we simply put that number here. And then we're going to add, because that's what summation means. You're adding. The same thing for water. It's 4 times. Be careful. It's liquid water. Be sure you use the right number. Liquid and gas would be different. So we come back to the same sheet. There's liquid water. Put this in focus. Setting up a little, that's why. That's liquid water is negative 285.8. We're going to close that parentheses, that's a negative, and close that block. So this is the products right there. Now we're going to subtract from that the delta H of the reactants. So another block, and here we go. Here's the reactants, and there's C3H8 gas. We come back over here. That's the one that we corrected for propane. So it's negative 103.85. And you have only 1 mole of it, so you don't need to put anything in front of the parenthesis. Okay, and then it's minus the enthalpy of formation. Now, if you read your notes of oxygen gas, if you read your notes, you'll see that the enthalpy of formation of a pure element is 0. All you have to do is write a 0 there. Has no official enthalpy of formation. So now we're ready to close that. So now we have a pretty long equation. You got to be careful you don't get tripped up on your negative signs. I recommend, unless you're really, really good with a calculator, and even if you are, do this in pieces, okay? So I'm going to say that 3 times negative, and remember that you have to use, for a negative number, you have to use this button right here, not the minus sign here, but this button for a negative number. So it's minus 3 times, let's go ahead and do it on the screen, minus 3 times, well, I can't see the number though, minus 3 times negative 393.5, like that. Now it's a PEMDAS, so it's going to do multiplications before it does this addition sign here. So I'm going to add, don't need any parentheses really, so I'm going to add 4 times negative 285.8. And I'm going to hit enter. And that's going to give me, for this right here, negative 2323.7. Now we're over here, and not much to do here except be careful of the double negative. It's going to be minus negative 103.5. You can ignore this, of course. And so that's going to be plus 103.5. And if you add that on, you get negative 2220.2 kilojoules. If that number looks familiar, that was the mistaken number that was put right. Get this to focus. That was the mistaken number. So that was actually the enthalpy of reaction for propane, not the enthalpy of formation. So this was the enthalpy of a combustion reaction, which is what we ended up with right here. And there's your final answer for that. Okay, let's move on to number 11. You'll notice I'm back to doing these on the sheet, and that's because you can see these don't take up very much space, unlike Hess's law, which could be a half a page doing a Hess's law method. So these are pretty straightforward. So we're trying to find the enthalpy of reaction of this compound with oxygen. Again, another combustion reaction. And this is ethanol, by the way. And so what we are going to do is go ahead and write our equation. So delta H, reaction, and now let's plug in our numbers. There's the reactants, the products over there. So let's start with those. So we have 2. And again, put my big block there for products, and then it's minus 393.5. That's the enthalpy of formation of carbon dioxide. So that's that right there. Then we're going to add to that for water. And it is liquid water again, just as in the last reaction. So it's going to be 3 minus 285.8. Again, you can either get this off the front page of this assignment or the purple sheet. These are all enthalpies of formation here, okay? So I should have pointed that out, that you don't have to get them off the front. So water is minus 285, liquid water. Ethanol, what we're talking about here is right there. We're going to write that one down in just a moment. Carbon dioxide right here, minus 393.5. So you get all those off that purple sheet. In Table C, Appendix C of your textbook, there's about a 2 to 3 pages, a very, very complete list of these. But you don't need to use that for this assignment. Okay, so we're done with the products. We're going to close this block. Now we're going to do the reactants. So this is ethanol, and there's only 1 mole of it. We want to be sure the reaction's balanced, but we got 2 carbons. Yeah, everything's good there. So we're going to make another block and ethanol. So this one wasn't on the front page of your assignment, so we're going to come over here, and we saw that that's negative 277.7. And there's only 1 mole of it, so I don't need to put anything in front. Close the parentheses. Minus that for oxygen, and as we already said, there's no enthalpy of reaction. The enthalpy of formation. The enthalpy of formation for a pure element is 0. We're just going to put a 0 there and close the bracket. Okay, and now you do the same math you did on the equation above. So we're going to say 2 times negative 393.5. Plus, again, because of PEMDAS, you don't need to wrap anything in parentheses. The multiplications will be done first. Times negative 285.8. We hit equals, and that means for our products, again, I'm a chicken. I don't want to do the whole thing in one calculation. It's too easy to make a mistake. So there's the products right there. And now over here, it's going to be minus negative again. Minus negative is plus, so it's going to be plus 277.7. And that's going to give us negative 1366.7 kilojoules for that reaction right there, for that combustion reaction. So that's you could call that a delta H of reaction, or you could call it a delta H of combustion. It just means of a combustion reaction. I'll just abbreviate that there. Okay, you could have called it either of those things right there, and that's your answer. All right. Next one up is hydrobromic acid. And let's see if that's on our purple sheet. If it's not, you got to go to the back of your book. But I believe it is. There it is right there, down at the bottom here on the first column. There it is. That's what we're looking for. All right, so let's go ahead and do this one. I would like you to write the equation, but I'm going to skip it this time so we can get going. Let's be sure we have a balanced equation. And it does not look like we do here. So let's go ahead and I'd actually asked you to balance it. So we have two O's on this side and one on this side, so I've got to put a 2 there. So now that makes my hydrogens 4. I know I'm not doing this writing my elements, but this is pretty quick and easy. That's going to be a 4 there. That means we have 4 bromines there, so we need 4 bromines over here. That means I have to put a 2 there. Okay, let's see if we're in balance. So we got 4 hydrogens, 4 hydrogens, 4 bromines, 4 bromines. You got 2 oxygens, and you got 2 oxygens. So everything's in balance. So 4, 1, 4, 1, 2, 2. Okay, so let's go ahead and do this. So I'm going to start off with my products over on the right. So it's 2 times, and it is liquid water still. So it's negative 285. You'll get to where you have these memorized after a few problems. Plus, and we have 2 times Br2. Br2 is a pure element, so it's 0. Okay, no enthalpy of formation for pure elements. Okay, so that's going to close this bracket, and we have 4, my big bracket there, and in parentheses, it's HBr. We just saw that a moment ago. It's negative 36.23 from the purple sheet. You got a lot of sheets now, but just practice, 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 and you get used to manipulating them, handling them, and moving them about. Okay, plus there's O2 again, and we know that's going to be a 0. So now we can close that bracket. Okay, and so now we got 2 times negative 285. .8, and that's going to give us negative 571.6, and then it's minus a negative here. So let's go ahead and write that number down. It's negative 36.23 times 4. That's going to be negative, it's going to be positive, excuse me, because the negative is going to become a positive, 144.92. And if you add those two numbers together, you end up with negative 426.7 kilojoules. Okay, and we're going to do one more of these. It says write a combustion reaction for propane. Well, you know what? You've actually already done that. Number 10 was propane, so I'm going to change that to ethane. And you can find that on your purple sheet, what ethane is. And ethane is C2H6. So we're going to go ahead and write a combustion reaction for C2H6. And if it's a combustion reaction, that means you react it with O2. And you're going to produce products of CO2 and water. Okay, so now we need to balance that. So you want to do that a little more formally than we did last time. We have a C, an H, and an O. On the left side, we have 2 carbons. On the right side, we have 1 carbon. On the left side, we have 6 hydrogens. On the right side, we have 2. On the left side, we have 2 oxygens. And on the right side, we have 3 oxygens. Okay, what's the easiest thing to balance that's not already in balance? Probably the carbon. So we're going to put a 2 here. We could do carbon, and we put a 2 here. The problem is you have to ask yourself, what else does that balance? It balances an oxygen. And since oxygen appears in 2 different locations, we want to avoid oxygen. So while there's nothing wrong with doing that, well, there is something wrong. You want to stay away from oxygen. First of all, it's a pure element. We talked about staying away from balancing pure elements until the very end. And then also it appears in more than one location. So even though carbon looks like it's the easiest to balance, we don't want to do it because of what it's attached to. It's attached to an oxygen. So let's stay away from that. Okay, so how about hydrogen? So if we do hydrogen, we have 6 on this side and 2 on this side. So if we put a 3 there, we now have 6 on this side. We come back over here, we got 6 on that side. And so we're stuck with balancing an oxygen. I'm just showing you some of the issues that can come up. So we will go ahead and do the carbon here. All right, and so we have 2 there, and we have 2 there, so that's all good. So the hydrogens are in balance, the carbons are in balance. Now let's see what's going on with the oxygens. So you have 2 times 2 is 4. Let me go ahead actually and update this. So we have 6 hydrogens, we have 2 carbons on this side, and 2 on this side. So the thing that's messy is the oxygen. So what do we have on the right side? We have 2 times 2 is 4 oxygens, and 3 times 1 is 3 more. So that's 7 oxygens. It's an odd number. That means we're going to be in that quirky situation where we need to come up with 7 on this side. So the only way to do that, since 7's an odd number, is call it 7 over 2. In other words, if you multiply 7 halves by 2, just do it. It's just a little fraction multiplication. You get 7, and that's what we needed. So that's going to be our coefficient. But this is not an enthalpy of formation situation we're talking about here. In other words, it's a combustion reaction. It's just a normal chemical reaction. So we're not allowed to have a fractional coefficient. So if we multiply everything through by 2, we get a 2 there. We multiply 7 halves by 2. This basically makes it 7, so that 2 goes away. We multiply this by 2, it becomes 4. We multiply this by 2, it becomes 6. For a balanced chemical reaction, I'll just go ahead and write it down here, is 2C2H6 plus 7O2 gives us 4CO2 plus 6H2O. Okay, let's be sure everything balances. We got 4 carbons and 4 carbons. We got 12 hydrogens and 12 hydrogens. And we have 4 times 2 is 8 oxygens, and 6 times 1 is 6 more oxygens. 8 plus 6 is 14. 7 times 2 is 14. So we have a balanced reaction. Okay, so let's go ahead and do this. So that we go with the products first. So it's going to be block 4 times CO2, and I'll use the purple sheet this time. Carbon dioxide, negative 393.5 plus 6H2O. And that's going to be a liquid in a combustion reaction. It has been in all the previous ones. So let's go ahead, let me go ahead and put our states in for all of these. Gas, and this is a gas as well. Okay, so it's 6, and that's going to be negative 285.8. And close that. So that takes care of our products. Now we subtract from that the reactants, and that's going to be 2 times ethane. So we come over here, and ethane is negative 84.68. 2 times negative 84.68 plus, and again, we have a pure element there, so it has an enthalpy of formation of 0. And that's your equation. So go ahead and just run the numbers on that. And here I get negative 3,288 plus, because the negative there, and that's going to be 169.36. So that's going to give us a delta H. And you can either write of reaction or of combustion, because it is a combustion reaction. Of negative 3119.4 kilojoules. Should put the box all the way around that whole thing there, okay? And that is our answer. Okay, now in this problem, there's an additional issue involved. And that is, when we figured out this enthalpy of combustion, it was for 2 moles of ethane. So now we're going to define another term. It's the standard enthalpy of reaction. And what that is, it's the number of kilojoules per mole. So what we found is we had negative 31, or 3,119.4 kilojoules in 2 moles of C2H4, so 2 moles. C2H6. Okay, so you do the division on that, and you get a standard enthalpy of reaction of half that number. And that would give you 1,500, and let's just call it 1,560, and again it's negative, and that's kilojoules per mole. Okay, so in balancing this reaction, we really didn't have to multiply through everything by 2 up here. We could have left it as 1 mole, 7 halves, 2, and 2, and if we had done that and then plugged everything in this equation, we would have ended up with this number down here. So that's something you want to think about when you balance the equation. Do you really want to multiply through, or are you okay with a fractional coefficient of 1 and 7 halves and 2 and 2? All right, but anyway, we got there simply by dividing by the number of moles of ethane that we had, and that gave us the standard enthalpy of reaction. All right. Okay, so I'm going to break this off right now and publish this video. I'm going to do it as both an MP4 and a YouTube for those of you that are having problems with the YouTube situation, because this video is at 1 hour and I want to get it up. This is a 2-day assignment. It goes until Tuesday, and we'll work on some of this in class. Ideally, you come into class having seen these problems, and then it won't be hard to work the rest of the problems from there. We'll also cover bond energies at that time, and do that. So I'm going to put this up, and then I'll work the rest of the problems on a later video. Okay, so see you on that later video.